we already used this concept of geocentric parallax, but we did not define it. We defined the annual parallax, which is the parallax having as base the orbit of the Earth and is due to the motion of the Earth and its orbit. But the geocentric parallax is the apparent shift of an object when seen by different observers on the surface of the Earth. As an example, imagine that the moon is occulting Saturn, with the center of the moon coinciding with the position of Saturn for a hypothetical observer at the center of the Earth. Now, the radius of the moon is 15 arc minutes. Will an observer somewhere else on Earth also see an occultation? Which are the parts on Earth that will see an occultation of Saturn by the moon, and which ones will not? So let's see what changes. So we have a hypothetical observer on the center of the Earth here, that's point C, and a star S. From the center of the Earth, the star S will have a zenithal distance. And then here you have two different observers on Earth. For this observer, the zenithal distance of the star S is different. This is the zenithal distance at the center of the Earth. This angle is the zenithal distance for the observer O. And for the observer O1, the star S is in the horizon. So geocentric parallax definitely matters. Now let's find out then how to mathematize it. So I have here the geometrical situation. For the center of the Earth, the zenithal distance, or the true zenithal distance, is Z. For the observer at O, you have that the zenithal distance is Z prime. And for the observer O1, the star is at the horizon. So let us call the parallax the angle Z prime minus Z, which is the difference between the measured altitude, or the measured zenithal distance, and the true zenithal distance as it would be measured from the center of the Earth. That's similar to what we did for the annual parallax, which was the angle as measured from Earth minus the angle as measured from the Sun. Now, let's use the triangle OCS, which is this one, and apply on this triangle the law of sines. Now, this angle is 180 minus Z prime. This is D, the distance. So from O to C, that's the radius of the Earth. And the parallax is this angle. So you apply the law of sines, and you have sine of P over A is equal to sine of 180 minus Z prime over D. So sine of 180 minus an angle is the same as the sine of the angle. So this is sine of Z prime over D. So you conclude that sine of P is equal to A over D times sine of Z prime. So you can see from this that the parallax is going to be greatest when Z prime is equal to 90 degrees. So this is called the horizontal parallax. So for instance, the horizontal parallax of the moon is the radius of the Earth over the distance of the moon, which is about 1 over 62, 67 minutes of arc. Now the parallax for an arbitrary zenithal distance Z prime, you can simply write as sine of little p. The parallax is equal to sine of big P, the horizontal parallax, times the sine of Z prime. Now, if both P and big P are small angles, as a parallax usually is, then we can approximate P, sine P by P, and then this becomes P is approximately big P times sine of Z prime, where the horizontal parallax is the radius of the Earth over the distance to the object. So let's go back to the example that I gave before, but instead of Saturn, let's use a star. So the moon is occulting the star Aldebaran, with the center of the moon coinciding with the position of the star. So Aldebaran has red ascension 4 hours and 36 minutes, and declination 16 degrees and 31 minutes. So the moon is occulting Aldebaran, with the center of the moon coinciding with the position of the star, at culmination for a hypothetical observer at the center of the Earth. Now the radius of the moon is 15 arc minutes. Will an observer, say from APO, see an occultation? So to find the solution, we need to find, after correction for the parallax, the disk of the moon, if the disk of the moon is going to be covering Aldebaran. The geocentric altitude of the moon, we can find it's the altitude is 90 minus the latitude of the place plus declination. APO is at latitude 32 degrees and 47 minutes. That's the latitude of Las Cruces. So this is 90 minus 32, 47 plus 16, 31. This gives you an altitude of 73 degrees and 44 minutes for the moon. So the geocentric distance, the geocentric zenith distance is Z is equal to 90 minus H, which is 16 degrees and 16 minutes. And the shift by parallax is the horizontal parallax times the sine of this altitude. Now, the geocentric parallax shift is the horizontal parallax times the sine of the apparent zenithal distance. Now, we only know Z, which is a true zenith angle, but let's take a first guess. Let's say that Z is approximately equal to Z prime, which is 16 degrees and 16 minutes as a first guess. If we put that into the parallax, we find the horizontal parallax of the moon is 57 minutes, and then times the sine of 16 degrees and 16 minutes, that gives you 0.266 degrees, which is equal to 15 minutes and 58 seconds. So essentially the same, 16 minutes. So you have to add 16 minutes. That would make the apparent zenith angle 16 degrees and 32 minutes. Now we can use this value of Z prime to refine the estimate of P. Let's recalculate then what the parallax is with this new estimate. Then you have the parallax equal to the horizontal parallax times the horizontal parallax, 57 minutes, times now sine of Z prime, 16 degrees and 32 minutes. Let's see if the 16 minutes will make a difference. That gives us, again, 16 minutes. So the value changed by 2 arc seconds only, from 1558 to 16. So 2 arc seconds is not much, so we accept the convergence of the geocentric parallax shifted to 16 arc minutes. So we concluded that the apparent altitude of the moon will be 16 arc minutes lower as the altitude seen by the hypothetical observer at the center of the Earth. Now, since the moon's radius is 15 minutes, its edge is going to be 1 arc minute away from Aldebaran. So an observer at APO will not see an occultation.